Okay, thank you. I'm here to introduce. Is the mic on? Okay. It's interesting how hard it is to tell from up here. I'm here to introduce our speaker today, but I actually have a pleasant duty to do before that. This is the annual PH lecture. The PH lecture is an endowed lecture established by the Hertlendi family of California. And in particular by Dr. Paul Hertlendi, who's our guest here today. He's an alumnus, Paul is, of the Smithsonian National Board. And for several years, while he was on the Smithsonian National Board, he was the National Board's liaison to SAO. So he came to know us pretty well. Not written down, but which actually was quite significant, Paul became the poet laureate of the National Board and was called upon for original poetry at their meetings. So Paul was very interested in understanding how careers develop in our field and encouraging young people. And so he established this lecture specifically to recognize the achievements of scientists early in their careers. And he graciously left it very vague what those words meant. So we had considerable latitude to choose people who we thought had done something really significant, but also relatively early in their careers. And there are a great many very well-known people on the list who've been PH lecturers. Sean Andrews, who's here on the staff. Gaspar Bakos, now at Princeton. T.J. Cox. Actually, I've lost track of T.J. Lisa Kaltenegger, Mukremin Kilic, Mercedes Lopez Morales, who's still with us, Smado Naus, Karen Oberg, who's still with us, Alexei Viklinin, who's here in the room and was the inaugural PH lecturer, and Matthew Walker. So what I'd like to do is I'd like Paul to come up and present the certificate to our speaker, and then we'll proceed with the introduction.
Brian, would you care to come out here? This is going to be the shortest, but not the least fervent, nor the least honest presentation. And I hope you can hear me in the back row. Can you hear okay without a mic? Okay, I'll read this off. The PH Award and Prize Lecture is hereby presented to Ryan Alderant, 14th of April, 2016, in recognition of exceptional contributions in enabling technology and creating mission concepts for X-ray astronomy, signed by the director of the Smithsonian Astrophysical Observatory. Ryan, it gives me great pleasure to present this to you.
Thank you.
And good luck.
So Ryan is a staff scientist here. He studied physics and mathematics at Illinois State University and went on to obtain a PhD in physics from the University of Iowa in 2012. While at Iowa, he took the lead on the development of the Bragg reflection polarimeter of the Gravity and Extreme Magnetism Small Explorer, or GEMS. And he carried out numerous observations using the Rossi data from the Rossi X-ray Timing Explorer and the SWIFT missions. He went on to develop reflection grating technology for X-ray spectroscopy during a postdoc period at Iowa State, and he joined SAO in 2013 as the first Leon van Speebroek Fellow in X-ray Optics. Since Ryan came to Cambridge, he's taken an ever more important and leading role in the effort that we have going here to develop extremely powerful optics for a future X-ray mission, which has now come to be known as the X-ray Surveyor. X-ray Surveyor has legacy from Chandra, but has a goal to be, depending on which figure of merit you use, 50 or maybe much more than 50 times more powerful than Chandra, an extremely ambitious goal. And he's going to talk to us today about steps towards achieving that. Mm-hmm. So with that, I'll hand the floor to Ryan.
Okay, thanks. So I'm going to start off by talking about technology development for the X-ray Surveyor, but I will also touch on technology development that we're working on for a medium explorer mission concept called Arcus, and that'll be the last third or so of the talk. Okay, so as Charles said, the X-ray Surveyor is a notional successor to Chandra. We're looking for roughly 30 times the collecting area while matching Chandra's subarc second angular resolution, although over a wider plus or minus 10 arc-minute field of view. As far as detectors are concerned, the plan is to use active pixel sensors for high-resolution imaging, microcalorimeters to offer improved energy resolution in the harder X-ray bands, and then using next-generation diffraction gratings to achieve high resolving power in the lower energy X-rays. And I should mention that X-ray Surveyor is a mission concept that has just convened a science and technology definition team, and that's a multi-institution team that is working to define the science case and the technology requirements for the mission. And there are multiple optical approaches currently being studied. So the optics that I'm going to describe are primarily a Smithsonian and Marshall Space Flight Center concept, but there are others. Okay, as an example of the kind of science that X-ray Surveyor can do, it can do a wonderful job in looking at X-rays from the epoch of reionization. And it can do so both with normal galaxies and then also galaxies with active nuclei. It's estimated that in the 4 megasecond exposure, we can detect galaxies with star formation rates on the order of 2 to 20 solar masses per year, and that's primarily via emission, X-ray emission from high-mass X-ray binaries. And then as far as active AGN are concerned, at a redshift of 10, the detected photons that X-ray Surveyor sees in the rest frame are emitted primarily in the 2 to 100 keV bandpass, where they are primarily unaffected by absorption. And so our 4 megasecond sensitivity corresponds to a progenitor black hole with a mass on the order of 10,000 solar masses. And this mass is right in the range that's predicted by various theories as to how these supermassive black holes first formed. Okay, so what I'm showing here are simulations for the James Webb Telescope, X-ray Surveyor, and the upcoming Athena X-ray Observatory, which is an upcoming L2 mission by the Europeans. James Webb will detect roughly 2 million galaxies per degree squared at its sensitivity limit, and that corresponds to 0.03 galaxies per X-ray Surveyor beam, which is not confused, and 3 galaxies per Athena beam, which is confused. Athena has roughly an order of magnitude worse angular resolution than X-ray Surveyor will. And so what this means is that X-ray Surveyor is uniquely qualified to identify progenitor black holes at these high redshifts. So this is an example of science that X-ray Surveyor can do that Athena cannot. Great. There's a whole host of other astrophysics topics that X-ray Surveyor should be able to address. And for the interested reader, I would suggest you look up the white paper that was produced from the X-ray Surveyor science workshop that was held last year in Washington, D.C., which is accessible by a Google search. Okay, so onto the optics. This cartoon, and you're going to have to bear with me. Those of you who went to the ITC colloquium will have to see a couple of repeated slides here. This cartoon shows the optical design of Chandra. There were four nested parabolic mirrors, and then they had matched 4 nested hyperbolic mirrors. The X-rays each went through 2 bounces and then were focused onto a focal plane CCD. Now these 4 shells were thick. They were fabricated with 1-inch thick zero-door glass shells, which meant that they were heavy and expensive to launch, and this limited the amount of area that could be collected. So the idea with X-ray Surveyor is to use thin, lightweight optics that can be tightly packed in order to maximize collecting area, for a given launch mass. There's various approaches. Some of them involve full shell mirror segments. Others involve segmented mirrors, azimuthally segmented. And this is the approach that Smithsonian is involved in. So the idea is to fabricate thin, lightweight mirror segments, align and bond them into mirror modules, and then take the mirror modules and align them into a full telescope assembly. And the idea is to do all of this while maintaining subarc second performance of the individual mirrors. So they have to maintain their performance after bonding and after launch. Okay. I've done some ray tracing work to come up with performance predictions for a notional X-ray surveyor design. We're using Wolter-Schwarzschild geometry. The mirror radii span from 0.2 to 1.5 meters. This corresponds to roughly almost 300 mirror shells and 8,000 individual mirror segments. Both the optical principal surface and the focal plane have a nominal curvature, a slight curvature. And this plot on the right shows the optical performance as a function of off-axis angle or field position. At the lower energies, below 1 keV, 1 keV and a half keV are plotted together, almost indistinguishable right here. And those show that we maintain subarc second position just about out to a 10 arc minute field angle. At the higher energies, we have our performance is not quite as good because at those energies, our performance is dominated by the inner shells, whose off-axis performance degrades more rapidly. I should note that stray light baffles were a key component to limiting the background signal for Chandra. And we need to do the same thing for X-ray Surveyor, but this is complicated by the fact that there are many more shells and they're spaced much more closely together. And so the same techniques that were used for Chandra, it's not clear that they'll work for X-ray Surveyor. So so there's some significant design work to be done on that area. Okay. Now, the Smithsonian approach to maintaining subarc second performance after bonding and after launch is to make them adjustable using piezoelectric material. So this cartoon gives the idea. We start with a 0.4 millimeter thick glass substrate, and that's shown here in purple. We slump that on top of a mandrel in an oven to achieve the Wolter geometry. Then we deposit a reflective coating on the front. This could be a heavy metal such as gold or iridium. And then on the back, we deposit a continuous platinum ground electrode followed by a 1.5 microns of lead zirconate titanate, which is a piezoelectric material, and then finally segmented platinum electrodes on top of that. And if you apply a voltage to one of these electrodes, that creates an electric field out of plane in this direction, and the piezo has the property that it wants to contract in plane upon the application of that voltage. So if you mount and align the mirror and you over-constrain it, the resulting deformations can be fairly well localized, and you can use this technique to control the shape or the figure of the mirror. We're also planning on developing strain gauge technology where we deposit strain gauges on each cell. A schematic of that is shown right here. And it's essentially a resistor whose resistance depends on the stretching of the surface that it's deposited on. And if you connect that resistor in an external circuit in what's known as a Wheatstone bridge, you can measure that resistance as a function of strain, and you can have an independent feedback mechanism to tell you how your mirrors are performing. A key aspect of technology development in optics is metrology. If you can't measure it, you can't build it. Well, in order to verify subarc second performance, we'll need to measure our mirror influence functions and surfaces to a roughly 10 nanometer accuracy. The the historical workhorse of the optics industry for this type of measurement has been interferometry. This schematic shows a Fizeau interferometer where you measure a surface by creating an interference pattern between a reference optic and a test optic. This creates a fringe pattern at a CCD. You integrate those fringes and you back out the figure of your optic. The problem with most conventional interferometers is that they have a limited dynamic range of a few microns. But to date, our prototypes haven't quite been at that level, and so we've needed an intermediate metrology tool to help us progress in the meantime. So we've developed a wavefront sensing metrology system, and the idea is that if you bounce a wave off of a deformed optic, those deformations become imprinted upon the reflected wave. So if you use a wavefront sensor, which can measure both the intensity and the phase of an optical waveform, you compare this with an optical telescope system, and you can measure test optics in a similar way to interferometry. So the optical design of a system to measure flats is shown on the bottom. You have a helium neon red laser. This hits a beam splitter and then is collimated with a lens right here. The wave bounces off the test optic, reverses its path, and then a field lens focuses the light from the test optic onto the camera. So the measurements are all done in reference mode. So to measure absolute figure, you first measure a reference optic with a known surface quality, shoot that wavefront, and then replace it with your optic of interest. More importantly, for influence functions, you simply measure your optic before and after the application of voltage, and then you can back out what the effect of applying voltage to a single actuator is. We've been getting roughly 1 to 2 nanometer RMS repeatability on surfaces with figures on the order of 200 microns. So this is interferometer quality measurements on surfaces that with a dynamic range a couple orders of magnitude greater. Okay, so we've done simulations to prove to ourselves that in theory this whole concept should work. What I'm showing here is distortion data from an actual fabricated and bonded mirror from the International X-ray Observatory days in the mid-2000s. So this is the axial direction of the mirror. It's 200 millimeters axially, 400 millimeters azimuthally. It's held at the axial edges, so you can see the bond points at the top and the bottom of the metrology data. And I'm showing this in slope space as opposed to surface height. So it's the axial derivative of the surface height. Okay, so then we measured, or we modeled influence functions using finite element analysis for a flight-like piezo cell pattern. And then we ran these through a bounded and constrained least squares minimization routine to determine the influence function magnitudes required to correct the mirror. And so I'm showing what the algorithm predicts the post-correction slope should be, but on the same color bar scale, but multiplied by 10, so that you can see the residual print-through ripple in the axial direction. And that's due to the periodicity of the cell pattern. The estimated point spread function goes from an RMS diameter of roughly 14 arc seconds pre-correction down to 0.4 arc seconds post-correction. So in theory, this idea should work. But of course, to get anyone to believe you, you need to fabricate these optics and test them in the lab. So our first shot at that was what we called our deterministic figure control prototype. A photo of that is shown here. This is a 100 millimeter round piezoelectrically adjustable mirror with this cell pattern deposited on the back with piezo adjustability. So the cells are 5 millimeters axially and 10 millimeters azimuthally. There were 86 PZT adjuster cells to work with, and the goal was to experimentally verify our ability to induce distortions to the mirror. So this is an example of the measurement of one of the influence functions. The measurement is shown up here, and you can see the 6 bond points in the metrology data. This is a modeled influence function for the same cell, and the two agree quite well, both in functional form and amplitude. Okay, so the next step was to try and induce a global shape change to the mirror. So somewhat arbitrarily, I chose a desired axial sinusoid to put into the mirror. This was a 0.3 micron amplitude, 50 millimeter period sine wave, which corresponded to a 5.4 arcsecond RMS slope on the surface. So then what I'm showing here are the residuals of what our algorithm predicts we should be able to do. So this is how well our algorithm predicts we should be able to match this figure. And so that residual is 1.7 arcseconds RMS. What I'm showing on this side is how well we actually did. So when I applied the voltages to the mirror that our algorithm produced, and then measured the surface of the mirror, and then subtracted our test sinusoid from that measurement, the residual was roughly 2.1 arcseconds RMS. But what the goal really was here is to determine how well the piezo adjustability is matching our model's predictions. And that's demonstrated with this plot, which is the difference between predicted minus achieved. And that ended up with a 0.9 arcsecond RMS error. So the induced figure matches what the model predicts to less than an arcsecond RMS slope error. All right. Now one can imagine doing this for all sorts of different frequencies, amplitudes, and phases of sinusoids. And so you can actually map out what we're calling a correction transfer function, where you choose an input sinusoid, you run the correction algorithm, you compute the pre and post correction power spectra of the mirror surface. So I'm showing in green, in log space, a roughly delta function sinusoidal PSD. And then in blue, I'm showing the post correction PSD. And there are higher order peaks here due to the print through ripple that I described a couple slides ago. So you can integrate these two PSDs and then take the ratio, and that becomes a figure of merit for how well you've reduced the power of that sinusoidal peak. You can do this as a function of frequency and map out a correction transfer function, which is your ability to correct the mirror as a function of frequency. So I did this for our flat DFC mirror, both using our modeled influence functions, and the result of that is shown in blue, and using the measured influence functions, and the result is shown in green. And there's a clear degradation of our ability to correct the mirror using the measurements. A specific example is shown on the right, a frequency of 0.06 inverse millimeters. This black rectangle shows the subaperture mask that I was using for my analysis. And this is the result of introducing that sinusoid using the modeled influence functions. And this is the same using the measured influence functions. And there's a clear distortion going on here. Okay. It turns out that the source of that distortion is mostly metrology noise. Very quickly after I ran the first sinusoidal perturbation experiment, I discovered that cleanroom blowers were increasing the variability of my influence function measurements, and so that was quickly eliminated. But we were still left with inherent wavefront sensor slope noise. Maybe it's not quite white, but the power spectrum of that noise looks quite flat. It's shown here in green. This is the power spectrum of measuring the DFC mirror surface and then measuring it again and subtracting the two with no voltage change between the measurements. So then in blue, I'm plotting the PSD of the residuals after trying to input a sinusoid. And the functional form of these residuals in power spectrum space matches the repeatability quite well. So our theory is that when our optimizer tries to create a linear sum of the 86 calibrated influence functions to correct the mirror, this noise stacks up and ends up limiting the ability of the optimizer to increase the voltages to reduce the low frequency figure error because the optimizer doesn't want to introduce too much high frequency noise. So this naturally leads one to conclude that you should try doing some frequency filtering or smoothing to the influence functions to correct this problem. I tried a low-pass brute force filter that ended up improving the results about 20%. And then in recent times, I've tried Savitsky-Golay filtering, and I will be looking at Chebyshev filtering in the future, and I will cover that a little bit more later in the talk. There's also been recent improvements to wavefront sensor software to permit more sophisticated averaging techniques, and so through a combination of all these efforts, we hope to reduce metrology noise as low as possible. Okay, so we're trying to build an X-ray surveyor, so we want to use Wolter geometry adjustable mirror segments. So they can't be flat; they have to be roughly cylindrical. So you need tools to measure cylindrical surfaces. So we're using a cylindrical null corrector to convert the plane waves of our interferometers and wavefront sensor beams into cylindrical waves. And so to do that, I'm using a computer-generated hologram, which is essentially a variable line space diffraction grating, which converts a plane wave into a cylinder. This is an example of an optical design for the wavefront sensor system for a 220 millimeter radius of curvature cylindrical optic. The CGH goes right here to convert the plane wave into a cylinder, and then you also have to include a cylindrical field lens to make sure that the image location matches up in both axes. Okay, so I have two of these in-house, one for a 200 millimeter cylindrical beam, one for a 1 meter beam, and they've both been tested with both systems. Okay, and this was in preparation for doing a cylindrical deterministic figure control measurement. So the same sort of thing that I showed you with the flat adjustable mirror, but this time using cylindrical geometry. So we were using substrates provided to us from our collaborators at the Observatory of Brera, and these were slumped glass substrates with 1 meter radii of curvature. Our collaborators at Penn State did the PZT processing on the convex surface and a stress-balanced chrome iridium reflective coating on the concave surface. And the idea was to bond these into a mount shown here, adapted from our alignment approach, and then to calibrate the influence functions and demonstrate our ability to control the mirror. Okay, so our first attempt occurred over the past month and a half or so. We're calling this the HFDFC sample, or high fidelity deterministic figure control. The figure of the cylindrical substrate had a peak to valley figure error of about 4 microns prior to PZT processing. We tried an experimental coding step to permit wavefront sensor metrology before we applied the PZT, and this resulted in a significant axial sag of the mirror after PZT processing of 150 microns. So I was able to adjust the wavefront sensor system to measure this sample, but the details ended up such that I could not make absolute figure measurements on the surface without doing stitching. Regardless, we did go on with the bonding process, the influence function calibration process, and the experiment to introduce a ripple into the mirror. I should also mention that roughly 30% of the cells were unresponsive due to problems, specifically a scratch in the electrode mask that Penn State used to deposit the cells. Okay, so I measured, so this photo shows the cylindrical adjustable mirror and the electronics used to control it. The mirror and its mount is shown right here. And this is a board we had fabricated in-house at Central Engineering to control each cell. 10 separate influence function measurements were made per piezo cell, and the result was taken as the pixel by pixel median. This was done in slope spaces because we optimized by RMS slope, so it makes sense to save the influence functions as axial slopes. An example of that is shown down here, and this black rectangle again is a subaperture mask used for analysis, both due to the fact that there were dead cells up here, and also the edge cells are less localized and have smaller amplitudes. And I also did frequency filtering to the IFs, which I'll talk about in a slide or two. Okay, so then I went forward, did an iterative sinusoidal perturbation on this mirror. And so this is the same experiment that I showed you for the flat sample, but I used a slightly different sinusoid, 0.3 microns amplitude, 100 millimeter period, which results in a 2.5 arcsecond RMS slope. So this is the test sinusoid plotted as axial slope that I tried to put into the mirror surface. This is how well our algorithm predicted we should be able to meet that surface. And there are dead cells right in this region, which is why we don't match it, which is why you see the systematic error right here. And then this is what we actually achieved. It matches the prediction quite well. And this achievement is the measurement of the surface after I apply the voltages output by our algorithm. And so you can see the high frequency noise in this measurement that was filtered out in our prediction. And so the prediction minus achieved has a residual of 0.45 arcseconds RMS. This is a factor of 2 better than what I reported for the flat sample. And a lot of that improvement is due to the blowers and the filtering that we tried. 2 iterations were generally sufficient. The second iteration improved the result by about 5 to 10%. And by that I mean we put in the first correction. There's a residual. You take that residual, run that through your algorithm, and then you come up with a perturbed set of voltages to get the correction to go all the way down to metrology noise limited. Okay. So I've mentioned that we need to remove metrology noise from the IFs to prevent stack up in the residual. If I do this experiment without any filtering at all, my residuals are about 0.7 arcseconds. The low-pass filter technique completely failed due to presence of cells near the edge of the mask. But then initial attempts at using Savitzky-Golay filtering with a rather arbitrary window size were promising. The results of Savitzky-Golay filtering on a single cell are shown here. Compare that with the raw data. There's an obvious noise reduction. But ultimately, our correction accuracy is limited by our metrology noise. In this geometry, that limitation is about 0.12 arcseconds RMS. And it's possible we might not get all the way down there. And if that's true, then we will have a degraded CTF, or a degraded ability to correct the mirror. And that then flows back into our requirements for our starting substrate. If you have a reduced ability to correct the mirror, it has to be better to begin with. And so the idea is that these things will flow together. We'll be able to use these experiments to come up with requirements for our starting substrates. Okay, so we're trying this again. We have a sample that had 5 micron peak to valley initial figure error. We have this in-house now. Penn State improved the mask that they used to deposit the electrodes, so we have roughly a 95% cell yield. We used an optical profilometer to measure the axial sag before the deposition of the front reflective coating. And then we computed the required thickness of this coating to remove residual axial sag in the mirror. So Penn State deposited that thickness. We received this roughly a week ago, and we used the optical profilometer to double check the axial sag, and it's about 15 microns peak to valley, or an order of magnitude better than the previous attempts. And so this will permit absolute figure measurement during the next round of experiments, which will be useful for demonstrating absolute correction of the mirror surface and also monitoring of distortions during the mounting and bonding process. And then finally, a realistic correction transfer function can be measured with this sample and then used to derive substrate requirements, as I mentioned a little while ago. Okay, so to summarize, X-ray Surveyor will offer orders of magnitude greater capability than the Chandra mission. We've developed metrology systems to monitor mirror performance. We've demonstrated correctability with a flat adjustable mirror, and it agrees to modeling within metrology noise. We've repeated this experiment with a 1 meter radius of curvature adjustable optic, and we've been able to reduce that noise by a factor of 2. And we believe that upcoming experiments with a new adjustable cylindrical optic will shed light on requirements for our pre-correction mirrors. And just to remind you, our objective here is, as a community, to demonstrate the feasibility of lightweight, high angular resolution optics to support the Surveyor concept. So, completely switching gears, or somewhat switching gears, I wanted to also talk about a medium explorer mission concept called Arcus. And this is a grating spectrometer mission. It's a multi-institution collaboration. The PI is Randall Smith here at SAO. And it's being planned for a proposal towards the end of this year. One of our key science goals is to measure the structure formation as imprinted in the outskirts of galaxy clusters, individual galaxies, as well as the intergalactic medium through absorption line spectroscopy. The requirements of the mission are similar to the International X-ray Observatory grating spectrometer. The effective bandpass is 10 to 50 angstroms, or 0.25 to 1.5 keV for those of you who like energy. The resolution goals are greater than 2,000 between 22 and 25 angstroms, which is the highly ionized oxygen bandpass. And then we want more than 500 square centimeters of effective area in that same bandpass. This is similar to the Chandra imaging capability, but used for spectroscopy. Okay, the grating technology that we're using to make this possible is called off-plane reflection gratings. So the idea here is that instead of your light coming in perpendicular to the grooves of a grating, you rotate that grating roughly 90 degrees, and instead the light comes in quasi or nearly parallel to the grooves. And so in this geometry, instead of getting diffraction in the plane of incidence like so, you get diffraction out of the plane of incidence in a cone. Okay, so just as with reflection gratings, in the classical geometry, you want to blaze these gratings such that you preferentially diffract light to one side of zero order. The grooves should all be radially grooved, which means that if you project the individual grooves, they should all converge down at the focal plane to a common point. And this is done to match the groove geometry to an incoming convergent beam from a Wolter telescope and to limit the aberrations as you diffract away from zero order. Finally, the alignment. So you're doing this in a reflection geometry where each grating has an angle of incidence on the order of 1.5 degrees. And so you have to nest these gratings into modules, just like you do the Wolter optics. And so the alignment of each grating must be such that their diffracted spectra overlap at the focal plane. And then any figure distortions of the gratings will create aberrations in the diffracted spectra, just as figure distortions in the Wolter optics would. All right, this is a schematic of the overall concept. You have X-rays coming in from this direction. You have grazing incidence, Wolter optics. We're using silicon pore optics provided by Cosine Research in the Netherlands. And so these optics, without gratings, would focus light down to this region right here. But the presence of diffraction gratings bring that zero order focus back underneath the footprint of the optical aperture. Okay, so what this looks like from above, so this is the optical aperture. The focus of this telescope should be right here. The diffraction gratings reflect this back underneath the footprint of the optical aperture. And then the diffraction occurs in this imaginary semicircle shown like so. And so we place a CCD array, shown here diagonally, to catch the relevant portion of the diffracted spectrum. We're planning to have 4 individual petals where 2 petals are co-aligned onto a single CCD array, although their spectra will be separated in the cross dispersion direction. Okay, so this is another view of the conical or off-plane diffraction. So these are the optics for a very small azimuthal segment shown right here. So there's a primary Wolter mirror, a secondary Wolter mirror, and then an off-plane diffraction grating. So the zero order the zero order reflection focuses right here, and then as the wavelength increases, the diffraction occurs in this semicircle like so. Now, because of the grazing incidence geometry, axial figure errors dominate the PSF, and they tend to scatter light in this direction simply due to the grazing incidence geometry. If you had a full shell, this would rotate about the nominal focal point, and it would look symmetric. But because we only use an azimuthal subaperture, we get this bow tie PSF. So the off-plane gratings diffract in this direction such that your resolution is dictated by the narrow part of the PSF. And so this is a technique that allows you to dramatically increase your spectral resolving power by about an order of magnitude. Okay, so these are my current predictions for the resolution and effective area for Arcus. We're observing light over 7 spectral orders. The most important is this 3rd order bandpass that offers resolution and effective area in the highly ionized oxygen bandpass. And we are getting well over 2,000 resolution in that bandpass and over 500 square centimeters. In the key part of the bandpass, we're getting almost 800. Okay, so to achieve this, as I said, the individual gratings need to be bonded and aligned with sufficient angular tolerances. These are tolerances in each degree of freedom as computed by ray tracing. The translational tolerances are fairly loose. We're talking about sizable fractions of a millimeter. So this is really an angular problem. And the tightest degree of freedom is roll of about 5 arc seconds, and that's rolling about the groove direction. So we're planning on meeting the translational tolerances with machine tolerances and mechanical constraints, and then using optical metrology to make sure we meet the angular tolerances. Okay, so we submitted a version of Arcus roughly a year and a half ago as a concept to be launched and installed on the International Space Station. And we got very high marks on our scientific case, but the technical review board had doubts about the feasibility of our optical technology. So to alleviate those concerns this time around, the University of Iowa and Smithsonian are collaborating to do an X-ray test of a silicon pore optics Wolter optics module, which is shown here, feeding a off-plane grating module that we populate and bond here at Smithsonian, and we want to demonstrate high resolving power in the X-ray band using the PANTER facility, which is in Germany. Okay, so this is a CAD model of what the optical setup will look like at PANTER. This is the optical axis of the chamber. The X-ray source is an electron impact X-ray source that is roughly 100 meters down the pipe towards the left of the screen. Then we mount in the pipe our silicon pore optics Wolter module, roughly a meter and a half inside the pipe. Then we mount and align our off-plane reflection grating module, and then this creates an arc of diffraction that we can that we can scan the PANTER detectors and measure resolution. Okay, so we're using a laboratory alignment approach because in situ X-ray alignment costs a lot of time and money. So if you can figure out ways to do optical alignment in the lab, this can greatly reduce cost. All right, so our approach is to use visible and ultraviolet metrology to achieve alignment requirements. And the idea is to bond into a module. This is a CAD of our module design. It includes 15 individual off-plane gratings. The housing is titanium. And then there are carbon fiber inserts with the CTE matched to the fused silica grating substrates. And everything's bonded together with flexures. The gratings are manipulated within this housing by a hexapod and then bonded into place once we meet the alignment requirements. Okay, so this is a setup, a schematic of our optical metrology. We're using a wavefront sensor, my favorite instrument, to measure the pitch and the roll and the figure of each grating. And then we use an ultraviolet laser that comes in the classical in-plane grating geometry, and that creates a reflected beam that we monitor with a CMOS camera, and then a back diffracted beam that we also measure. And that allows us to measure the yaw angle, or the rotation about this axis. Okay, so the module is on an indexing platform. So this is a photo of our current setup over at CDP. This is the hexapod, and the hexapod controls the alignment of individual gratings within the housing. The housing is bonded to this platform, which is on rails that have the 12-meter focal length radius machined into them. So the entire platform can slide on these rails. And so we index the platform such that each inserted and aligned grating occurs at the same physical location. So you align and bond. You align and bond the first grating, index the module, and put the next grating in the exact same place. Okay, so the UV laser technique is based on what was used for the XF high energy transmission grating period uniformity measurements. They did a similar setup where they inserted a laser beam, monitored the location of the back diffracted and reflected beams, and scanned the surface under the beam to measure groove period non-uniformity. And so we can use a collimated 266 nanometer wavelength laser, and that produces a back diffraction with our 160 nanometer groove period geometry. I've calculated that a roughly 30 arc second yaw produces a 60 micron shift of the diffracted spot, a reasonable distance away from the optic. So this should be easily measurable. And we've done some initial testing that shows that this should be doable. I've got a UV laser mounted on a hexapod right here. This is shining the UV laser down to a diffraction grating that's sitting on our optical bench, and that is the back diffracted UV spot fluorescing off of a white piece of paper. I've also measured our ability to centroid the spot from this laser with very minimal effort. We demonstrated that we could do that to less than 20 microns over a 600 millimeter or 600 micron total spot shift. So we're very confident that the yaw measurement technique should work. Okay, so wrapping up, Arcus is a near-term possibility for X-ray astronomy. If selected, it could launch in the roughly 2025 timeframe. We're going to submit this proposal towards the end of this year. The optical design promises over 500 square centimeters of effective area with high resolving power in the oxygen 7 bandpass. And in order to make this a attractive proposal, we are currently making steps towards an off-plane grating module resolution demonstration planned for this September to achieve grating TRL5 status. And that's it.
Talk is now open for questions. Well, let me start. So, in the first part of your talk was your fiber actuated mirrors. When you actually get to the finish line, I'll say
about to launch. At what stages what's the last moment at which tweaks can be made to a surface?
I think it's what's the last moment that you can measure the surface, and the current idea is that you have these nested shells, right? So you begin aligning and bonding in the outer shell, and you calibrate all the influence functions, you calibrate the figure error, you store those in lookup tables, but then as you populate the telescope, you'll have mirrors that block those off. And so I think at that point, it'd be extremely difficult to measure the surface. So I think you have to be pretty confident that, that you have to take measures to make sure that nothing changes after that step.
Including launch and vibration and all of that?
Yeah, so
vicious stuff that happens.
Yeah, so lots of environmental testing happens, vibration testing to make sure that the mechanical design is valid, the bonding techniques can hold, and the thing won't shatter.
Yes, right.
So there are no plans to have on-orbit wavefront sensing of any sort?
Nope. It's too difficult. I mean, it's been thought about, and it just doesn't seem feasible. Dan Schwartz will talk your ear off about that, and tell you
That's
about
why you're
it.
really unhappy right now.
Well, what you can do is actually you can calibrate modules on the ground with so-called ring imaging. And when we studied a Generation X 10th arcsecond telescope 15 years ago for a vision mission, we did imagine flying such a system with detectors that move up in front of the telescope and get the beam as it's converging. So you separate each of 300 different rings and you move around and you measure them all. So for the telescope of the 50s or 60s, that's probably what will be done. But we're frankly trying to meet a price point here as well.
Well, we're so used to acronyms of everything. I presume Arcus is an acronym or has an acronym.
It's not
How
an
about the
acronym.
Surveyor? Sorry?
It's not an acronym.
No.
It
How
is
about the X-ray Surveyor? Are you thinking of one right now?
I'm not. I think that'll happen 20, 25 years from now.
No, it's a good thing you're young. Rhino.
Yeah, so how far do you think this technique or this adjustment, you said 0.4 arcsecond is kind of where you're aiming for. Do you think ultimately, like thinking further ahead, this can be pushed down to like below 0.1 even, or are there some really fundamental points where at some point you have to go to a different technique?
I don't know what the ultimate fundamental point will end up being, but I don't think that 0.4 is the limit. That 0.4 limit is currently constrained by our expected performance of the starting substrate. So if we can improve that, then we can, the correction is to a large extent linear, and so you can bring it further down if you start out with a better substrate. But it's not clear how much better we can make the starting substrates beyond 10 arcseconds.
Jeff?
So what do you think are the greatest challenges you have to meet by the decadal? And what are the most difficult problems that you face in achieving this?
Yeah, okay, so I think fabricating slumped glass substrates of the sufficient quality, that's one technical milestone that we have yet to achieve. We have solid plans for achieving that. We're about to get some technology in-house in the next few months to meet that goal, but I'll be very happy once that's met. But then also stress balancing. We're depositing a lot of things on both sides of the mirror, and so we need to be sure that the combined stress effect of all of those layers leaves us with a mirror that's still good enough. So a lot of work we need to put into balancing stress.
So you mentioned that there were a number of competing approaches being developed. Is there one out there that you're most worried about in terms of the competitive landscape?
No. So the advantage of the piezo adjustability is that it is hybridizable. So there are, for example, Marshall Space Flight Center is doing differential deposition, where they take a sputtering beam and they fill in the valleys of the mirror. Well, there's no reason we can't make that mirror also adjustable and combine the approaches. And we actually have a proposal that we submitted to do just that. So most of the technologies that are out there can be combined into a collaborative approach to meet this goal. So I think that'll end up being the route we take.
Okay, if there are no more questions, let's thank Ryan again.